All right, how's Monday going?
It's Monday.
It's Monday. Not quite the same as Friday, but we're here, which is good. So my goals today are, first of all, I want to go over ODP 204, which was the one that was due on Saturday, and also PA1, make some comments on that, and any questions on that we can talk about. There was no ODP assigned for tomorrow. I'll post one tomorrow morning, but it's going to depend on what we do today. So I want to get through that first. So I want to go over this stuff, and then I'm going to spend the bulk of the class talking about the idea of allocating memory, and two ways that we can allocate memory, what are called static and dynamic memory allocation. And I want to talk about what those mean and describe how most of what we've been doing is static memory, and we want to move towards dynamically allocated memory. So that's going to be the bulk of what we talk about today, and that's going to bring in some discussion of the star, ampersand, the arrow, and all these weird symbology things that we do in C. And I want to probably spend part of tomorrow talking about these details and sort of make sure we're all up to speed on this. I know you've seen a bunch of this in 121, but I want to make sure we have a refresher so we're starting from a common base. So this will be the bulk of it. So before I get into all of that, any questions up front, including PA1 questions, ODP questions? Yeah?
What are some common questions that you get with PA1?
Oh,
Good way to put it.
yeah, so one common question is just sort of like, what does it all mean? Where do I begin? I don't understand any of this, right? Which is a fairly natural position to be in, because this is very different from most of the other programs that you've probably written, certainly in 224 and probably in 121. Most of those programs are basically kind of like turn the crank. We're going to just sort of put these things in and do these calculations and get an answer out. And PA1 is really building up a structure in memory. That's the essence of this course, data structures. But depending on what the person puts in, what we do to memory is going to be very different. And it's not just sort of performing the same calculations and coming up with an answer. It's really sort of placing things in this array, in the case of PA1, in different locations depending on what order the person decides to add and delete as they're running the main program. So it can feel kind of like this big fog where it's just, I don't really know what's going on. That's okay. Don't fight that. Don't try to make it look like, a program for calculating mortgage. Think of it as something different and just sort of work with it. Work with it in the pieces we've described, and it should start to make a little more sense. But it's only going to be more comfortable as you work with it. And this is why I say things like, make yourself a list in a bunch of assignment statements and work on your print function. Because even though print is pretty straightforward, it requires you to get into this mindset of, okay, I don't know what these structures look like internally. I have to tell my program how to figure that out. And it'll force you to start, here's a sentinel, this is what it's pointing to, this is what it's pointing to, this is when I know I hit the end of the list. And then you got your print function, but you're also getting more comfortable with the concept. So now if you go on to add or something, that's going to be a little easier. I should tell you that, so the init function you've probably already done. That was an ODP, right? The add function is the most challenging because it's got edge cases to deal with, because it's dynamically allocating new nodes and so on. The print function is probably the most straightforward. It's the first one we did the pseudocode for last week, but it's also the most useful in terms of developing these others. Because if you want to develop your delete function next and you make a bunch of assignment statements to create a linked list in memory, you can call your print function and say, what's my list look like? And you can make sure that you created the list correctly. And then you can call your delete function, delete node 7, and then call print again and make sure 7 is gone. And once you've got that working, you can do your search function. Build a list with 7, search for 7, it should be there, call delete, that's working. So delete the 7, now call search for 7 again, make sure it says it's not there. And then somewhere along the way, you get a good night's sleep, you got good music, go ahead and jump into the add function. And if you've done search, and you've done delete, and you've done print, add is just more of the same. There's two pieces to add. The first piece is moving through your list until you get to the node, the place that you want to insert. That's basically your search. And so the only new piece to add at that point is adjusting the pointers on the prior node and on the new node. So it keeps it in small pieces. And that's the name of the game here. You always want to be tackling a small piece. In the back of your mind, you're tackling a huge piece, PA2, PA5, whatever. But the current task you're working on is usually some smaller, more manageable piece of that. Right, that's what you're going to do your whole lives in programming. Someone's going to say, okay, write me some code to do such and such. Huge task, going to take you 6 months. But you're not going to go in every day and be working on this 6-month task. You're going to go in, you're going to be working on this 2-hour problem. And when you finish that, you're going to work on another one, and you're going to get all these little pieces, and now the next day you're going to go in, you're going to work on another 2-hour problem, which is putting these pieces together that you've been developing for the past few weeks. And when you finish your 6-month project, it's going to be at the end of, a 2 or 3 hour coding session, because you've got all these other pieces. Or, other people on the team have built those pieces, and you're putting those together with your code. So always be thinking about breaking problems down. Okay, essence of programming. All right, well, since we're into PA1, let me make another comment here, something to sanity check your coding on. Our array that we're dealing with, it's an array of struct nodes. We're setting it to have 100 locations. So what's the address of the last location? 99, right? It's always one less than the size because we start from 0. And our usual 3 fields: data, next, and valid. In your code, the only time you should ever be dealing with the valid field is in these two functions, getNode and releaseNode. And init, but init's not. Init's a special case. So getNode is trying to find an entry in this array that's available. And to do that, you start here after the sentinel and you search until you find a valid flag of 0, return that index. To release a node, if you want to release node 1, just set that entry to have a valid flag of 0 that says it's not in use. But those should be the only pieces of code that are dealing with the valid flag. In particular, your add function, your search, your print, your delete should never mention the valid field. Okay, that's really important for where we're going with PA2. Yeah?
What if checking if it's valid? We're checking if it's valid 0 or 1.
So who would be doing that check? Like where in your code?
The search number? The search algorithm?
Should not have to. Because how do we search for something? We have a sentinel, and we know the sentinel is always there. That's the beauty of a sentinel node. Okay, we don't care what the data value is, but it's always a node. In our case, it's always at location 0. And that points to a node, and that points to a node, and that points to a node. And so here's a 5 and a 15 and a 37. And this last one has this magic pointer value of myNull. So you want to search for a 7, start at the sentinel, see what node it points to. You know whatever node it points to is valid, because you're not going to put invalid nodes in a list, right? So this points to this node, check if that's a 7, it's not. That points to this node, is that a 7? No. That points to this, is that a 7? No. Where does that point? Nowhere. It's at the end of the list. You didn't find a 7, it's not in your list. Nowhere did I have to use the valid flag. Same thing with delete. If you're deleting, you're starting at the sentinel, you're just following these pointers. And you know that any node that you're pointing to must be valid. We're not going to put a node in our list unless its valid flag was 1, so we never have to concern ourselves with the valid flag. Yeah?
Is that the same thing with printing?
Same thing with printing. How do we print? Start at the sentinel. Where does that point? This node, print a 5. Where does that point? This node, print a 15. Where does that print? This node, 37. Where does that point? Nowhere. We're done. No mention of valid. And this is this idea of an interface, right? Our interface to the linked list is precisely these 5 functions.
So what is the point of the valid field?
The valid field is used internally because these functions are going to call getNode, for example, when you're adding to a list. You're going to say, I need a new node. You're going to call getNode, which is going to tell you where in your array to store that new node. Okay, the getNode function has to look at the valid flags because it needs to know, hey, is this node already in use? Valid is set. Yeah, that's in use. What about the next spot? Oh, valid is 0. This spot's available. So getNode will set that to a 1 to say it's in use, and it'll return the location of that. And so your add function just says, get me a node. GetNode says 7. And add says, okay, I'll store my new node at location 7. And when you delete a node, you delete the node at location 15. You'd like to set the valid flag to 0. Don't set the valid flag to 0 and delete. Call release node, pass it a 15, and let release node do it. And you'll see why I'm insisting on that distinction in about 15 minutes.
And you said release node does not interfere with valid statements?
Release node does. So these 2 functions are the ones that tinker with valid. Get node sets valid to 1, release node sets valid to 0.
Are they basically the opposite of each other?
Exactly, yeah. So once we've gotten a node, if we want to ungot it, we pass its index to release node. And so this bold-faced thing here, you must use getNode when determining where to create a new entry, and you must use release node to set the valid flag, to reset the valid flag after deleting. Yeah?
What's the parameter on release node? Is it the index or the data value?
The index. Yeah, I should call it index instead of number. All right, other questions on that? All right, let's do a quick run through. Let me just show you some code for ODP 204. So 204 was not actually part of PA1, but it's working with this array, right? This array of struct nodes. It's working with this as if it actually stored a linked list. So ODP 204 was basically saying, okay, here's my array. Show me what the first data node's value is. In this case, if I called ODP 204 and this was what my array looked like, it should return a 5 because that's the data value of the first node. So there's 2 possibilities. You can have the sentinel pointing to a node, which may point to another node, or maybe the end, in which case you want to return the value of that first node. Or it could be that you have an empty list, and the sentinel's next field is null. And there's nothing in the list, so there's no first node to return the data value of. Okay, and in that case, you just return a 0, but that's an error condition. So there's this second argument, error, and we set that to 1 or 0 to indicate if something went wrong. So if there is a data node, set error to 0 and return the data value of that first node. If the list is empty, set error to 1 and return a 0. So that was the goal. And here's some code that will do that. Struct node, the usual definition. I went ahead and declared my null to -1 just to get in the habit of that. And here's the getFirst function. So it takes a pointer to a struct node, that's the array, and it has a pointer to an integer, that's our error variable. And it's just those 2 cases that we just described. If the linked list's sentinel node, that's element 0, if the next field of that is my null, the list is empty. So set the error flag to a 1 and return a 0. If that's not the case, the sentinel does point to a data node, so there's no error, set the error to 0. And where is that data node in our list? Well, the answer is the sentinel's next field. So I take LL bracket 0, that's a sentinel, take the next field, and I store that in a new integer called index. That's where the first data node is stored. And then I said take element index in the linked list, give me its data field, return that. So while this isn't part of PA1, this is the kind of stuff that you're writing in PA1. PA1 is just a bunch of things that look like this. In particular, taking an index, grabbing that element in the linked list, and accessing a field, the data field, the next field. And so the pseudocode we went through last week, where we were saying temporary.next or previous.data, those get replaced with things like this, LL bracket previous.data. All right, so no ODP due tomorrow. Tomorrow morning I'll post 205, and it'll be due Wednesday. And it will be part of PA1. So let's talk about memory allocation. So far we're building a linked list. We don't know what this list is going to look like ahead of time. It may be that the user is going to add 10 numbers to our list and then delete 3 of them and then add 20 more. Or it may be the user is going to add a number, delete that number, add another number, delete that number, add 2 numbers, delete one of them. We don't know what they're going to do because there's this main program in front. They can say add this, delete that, and so on. But whatever they're doing, we're building up this structure of nodes pointing to nodes pointing to nodes. Okay, so PA1, how do we store that structure in memory? We make this array of these things called struct nodes, these things with 3 pieces to them, and we say that array is going to hold 100 struct nodes. So somewhere in your main program, you probably have a statement like this. Struct node LL bracket 100, or whatever you call your linked list. Well, that works well for PA1, because I'm not going to add more than 100 things to your list. But this is not really desirable. And there's a few issues with this. Issue 1, you've got to know ahead of time that 100 is big enough. When you say struct node LL100, well, our first entry is our sentinel node, so the person can add at most 99 things to their list without deleting anything. They can add 10, delete 10 forever. But if they add 99 things, this whole array is going to be full. And if they try to add one more thing, they're going to be out of space. Get node's going to return my null, and your code is going to say, sorry, I can't add that new number. So how big should this be? Well, we can make it 100. But maybe someday it's going to have to be 10,000. Maybe one day somebody's going to insert a bunch of stuff. So we could make it 10,000. Maybe someday somebody's going to want to insert 1,000,000 things into your list. So maybe we should make it 1,000,000. So this is the first problem. We don't know how big this magic number should be. We could make it ridiculously big. We could just set it to 1 billion, and probably nobody's going to insert 1 billion things into your list. But then, when the program starts to run, the compiler has set up the code to say, okay, find me space for 1 billion struct nodes and allocate that to this variable called LL. And you run your program and your system memory goes meow, and probably your system crashes because it's a memory hog. So that's not great. The second problem, remember how arrays work. Wherever this index 0 element is stored, index element 1 comes right after it in memory, and index 2 comes right after 1, and index 500 million comes right after index 499 million, etc. So when we do this, we're not just asking for a bunch of memory, we're asking for a bunch of consecutive memory locations. And allocating 1,000,000 bytes of memory is doable. Allocating 1,000,000 consecutive bytes, that's really hard. Because lots of things use memory, and memory is generally fragmented. This thing's using this chunk of memory, and it's also using this chunk down here, and something over here is using this piece in the middle, and it's all kind of scattered around. It's like your hard drive. It's very rare if you have 500 gigabytes free on your hard drive that it's actually one continuous block of 500 gigabytes that's free. It's a little bit here, a little bit there, a bigger chunk over here, and so on. Same thing with memory. So this requires consecutive memory locations. That's really hard to do. So this is static allocation. Static, not necessarily the best word, but static in the sense that the compiler decides we've got to allocate this memory in the beginning of the program. And when you run your program, before your code actually starts executing, the system tries to find this chunk of memory and sets aside space for that. So there's a pretty harmless program. It allocates 100 integers, gives values to the first and last ones. What could go wrong? Right? Not a big deal. Doesn't do anything, but it doesn't do any harm. Let's make an array of 1,000,000 integers. And I'll give some values to the first and last elements. Not too bad. Let's do 1,000,000,000. There's our segfault. And what happened is the compiler set up code, so when we start our program, it tries to get this chunk of memory, and it's not able to allocate 1,000,000 bytes times 4, size of an integer, in consecutive memory. And the memory system says there's an error, and our code says segmentation fault. So we'd like to get away from this idea of using an array to store our information. And everything else we do in this course, PA2, which is still a linked list, but then we're going to go on to trees and stacks and queues. All the structures we develop in this course, we're going to do this dynamic memory allocation. And dynamic, different word for that might be runtime. So statically allocated we can think of as compile time allocation. Dynamically allocated we can think of as runtime allocation. Static is compile time, and dynamic is runtime. I should just call them compile time and runtime, but most stuff you'll find out there says static or dynamic. All right, so what's the idea of dynamic allocation? Dynamic allocation says I'm going to want a struct node at some point, but when I'm running my program, that's when I'll decide where this is going to be located in memory. And when you do this integer x bracket 100 struct node LL bracket 100, you're saying right now, before I even start running my program, give me a chunk of 100 struct nodes. Dynamic allocation says, okay, I'm going to start off, I'm probably not going to have any struct nodes. But when I need one, I want to go ahead and find some memory space for it. So we're going to allocate this memory as we're running. And there's a few ways to do this. So let's talk about integers instead of struct nodes, just to keep it simple. So basically, instead of saying integer x, we're going to say integer star x. X is a pointer to an integer. And we can set the thing that x points to have a value. So let's make it more interesting then. So we'll store 98660. So we can call printf and say, show me the value that x is pointing to, and we'll pass star x as the argument to printf. As soon as you use printf, you need to have standard I/O. So I can't be too lazy anymore. And if I run this, I get my seg fault. Okay, from this point forward, when you start getting seg faults, think GDB. So recompile with a -G switch, or just always compile with a G switch. It doesn't do any harm. And let's say debug M1. So we're about to execute the first line of our program where we assign a value to the thing pointed to by x. And we know we're going to get an error either here or in the print statement. Print out the value of x. Guess what? It's a 0. Why is it a 0? Well, if you look at your program, did I give x a value? No. I told the compiler x is going to point to an integer. That doesn't actually give it a value. And then eventually I say the thing pointed to by x gets a value, but I never gave x a value. And on this system, it turns out x defaulted to a 0. On other systems, it might default to some crazy value. But if I look at what's stored at location 0, I get an error from the debugger saying I can't access memory location 0. If I try to examine location 0, I get an error, cannot access memory address 0. So by design, memory location 0 usually does not exist. Why? Exactly for this reason. Because a really common error is you forget to initialize something, and it ends up having a 0. And if you use that to access memory, this ensures that instead of accessing memory and getting some random value, you'll get an error and your program will stop. And it tells you right away, hey, something's wrong right here. And the problem in this case is x doesn't have a value. So what should x point to? What value should it have? 0 is not going to work. So how do we fix this program so that we don't seg fault? Well, we need to figure out what a good location in memory is. I don't know. We could try 1, but that's going to seg fault too. We could do the cat dance on the numeric keypad and pick a random address. Probably not going to work. So here's one thing we can do. When I say integer mynum, I'm asking the compiler, find me a location in memory where I can store an integer called mynum. So when my program starts to run, mynum will be stored somewhere that's usable in memory to store an integer. So I could say x equals the address of that variable mynum. So compile that, debug it, step through it. Now if I print x, it's something that looks like a normal memory location. If this looks like a normal memory location, you've been in this course too long. But it does. right? 7 with a bunch of F's and then some hex at the end. That's a good memory location. And if we print if we examine that memory location, it's got 5555. Why? No reason. It's just random. But we're about to say store 98660 at that location pointed to by X. So let's go ahead and execute that. And now if we print what's at that location, it's 18164. Well, that's apparently our zip code in hex. Or Vancouver zip code. But if we go ahead and we do the printf, we'll see X points to the value 98660. So this is a way to deal with runtime allocation, but not really. It was a bit of a cheat because, yeah, at runtime we gave X a value, but what value did we give it? We gave it an address that was already allocated by the compiler, or the linker. Okay, here's what's wrong with this approach. As we're building our linked lists, as we're coming through and we're saying, okay, I want to add a new node, so create a new node somewhere, set up a data value, change this pointer, change this pointer. We're going to execute the same code. It's always the same instructions in our add function. But the first time we call add, we wanted to create some node here. The next time we call add, we wanted to create a node at some other location in memory. And then adjust the pointers and so on. Well, this code is not going to do that. Anytime I run this code, X is going to point to this integer mynum. And if I come back in and I run this code again, right, if I had this executing multiple times, it's always going to point to the same value. So let's just throw a loop in here. And it looks silly, right? Because every time I do this, X is, E59C. And I keep doing this, and X is still E59C. And I'm storing this 98660 a bunch of times, but it's always getting stored in the same location. And if we do this in our linked list code, we're going to add a bunch of nodes, but they're all going to be stored in the same location. Well, that's not adding nodes, it's changing one node. And our list is going to look really weird. So how do we get an address at runtime to give to X so that we can store things in different locations? Does anybody remember this from maybe 224, maybe 121? Malloc, your best friend. So Malloc memory allocation. Okay, Malloc is used to say I want to allocate some memory while the program is running. And it takes a single argument, which is the number of bytes that you want to allocate. And it returns the address of the first byte of that chunk of memory. So let's tweak this program a little bit. Let's get rid of this silliness with mynum. And instead of setting X equal to the address of mynum, let's set X equal to Malloc. And how many bytes we need for an int? 4. So we'll Malloc 4 bytes. And we'll set X equal to... I'm going to store our zip code in hex so it looks nicer in GDB. And Malloc, you need to include standard lib. That's where it's set up. So compile that, go ahead and run it. So now if I print out X, well, it's a different looking address. It's a bunch of 5s and it ends with 6260. And so it should store 98660 at that address. So if I print the thing pointed to by X, well, that's decimal, but that's 98660 in hex. Let's examine this memory location. All right, there's 98660. So I said next it's about to do x equals malloc 4 again. Let's go ahead and do that, and let's print out x, and it's a different number. It's 56280. And so now when I execute this thing which says store this number at the address pointed to by x, it's going somewhere else. It's going at location 280 instead of 260. And I do malloc again, and now it's 2A0. It's a different location. And when I store my number at that location, it'll be stored somewhere else. So let's go back and examine that original location again. There's the number that we stored that first time. The next location is 0, 0, 0. 21 is just random. And now if we get to location 6280, there's our second copy of 98660. And there's our third copy at 2A0. And there's a bunch of zeros, but that's probably where it would store it if I did this again. And we can do something like examine /32 and say I want to look at 32 of these 4-byte locations in memory. And you can see more easily here where our things are being stored, right? Our first malloc gave us this location. That's where it's stored our integer, but it's got a whole bunch of extra space there. The second time I asked for space for an integer, it could have stored it right here, because that's not being used. But instead it decided to jump forward 32 bytes and store the number down here. That's what malloc does. Because mallocing is expensive. Right, in PA1 to malloc we need to go through our array of struct nodes. We need to check the valid flag, find a spot where it's 0. That's an expensive operation. Malloc is more efficient, but still expensive. It's got to find space, it's got to update some internal structures to mark that space in use. It doesn't want to malloc just a single byte or a single integer worth of bytes, 4 bytes. It allocates chunks. So 32 bytes seems to be the minimum. It's also nice to have things sort of starting at nice powers of 2. So all of these addresses that you get back from malloc will end with a 0 and actually have an even number in that second digit. All right, so I can run this program forever and it'll just keep allocating memory until my machine crashes. So I won't do that. But malloc will just keep finding different locations. And that seems to be as far as it ran. All right, making some sense? Yeah, so don't run this outside of the debugger because it'll slowly chew up your memory. When you exit the program, the memory gets freed automatically. But depending on your operating system, it can allocate so much memory that you can't actually get it to respawn to like a Control-C. And that's a bummer. But if you have your own Linux system, it's fun to play with. Have it print every like 10,000 times or something and see how long it takes and watch your memory go down. All right, so next thing I want to do, let's get rid of this magic number 4. I asked how big an integer is. Most people said 4. That was correct today on this machine. On a PIC processor, the answer would be 2. On some other systems, the answer might be 8. 5 years from now, the answer might be 8 always, or it might be 16. So 4 is a magic number. It's how big I think an integer is. But I don't know what machine and when this program is going to be run. So what we really want is however many bytes we need for an integer. And the compiler knows how many bytes an integer needs. It's got to know because it's got to set aside space for them when you say integer x. So the compiler gives us the option of saying size of parentheses, and this is a type of variable. So for example, size of int. And on this machine today, if I say size of int, the compiler replaces that with a number 4. So I'm going to say malloc size of parentheses int. One of the first things the compiler is going to do is replace that with a 4. And it's going to malloc 4 bytes. But it saves you from having to worry about it. And then if I take this code and I port it to an old 8080 processor and I run it, it'll malloc 2 bytes because integers on there were 2 bytes. So I'm going to try to save you some pain down the road. And some of you this will work and some of you it may not. But eventually this will become internalized, and then life will be pain-free. This should always be a type of a variable, not a variable. Int, car, double, struct node star, int star. Those are all types of variables. So a type of a variable is something when you're declaring a variable, you say type space variable name, int space x, struct node space ll. Okay, anything that you can put in there that defines the type of the variable, that's a good thing to put in size of. Variables themselves, don't put them in here. You can get away with it sometimes, and sometimes you can't, and the compiler will not tell you what the difference is. So unless you really understand what's happening when you put a variable in here, I would say just avoid it. For this course, don't put anything in here except a type. Except today, because we're going to break it. So I'm going to write some code that does nothing. So I'm prototyping a function called myFunction. It takes an integer array. My main program declares an array of 100 integers, and then it passes that to my function. And my function takes that and it just sets the first element to 1, just so it does something. And I'm going to compile this with a debugger. All right, so I'm in my main program. I'm about to call a function. Let's print the size of, and let's do what I said not to do. Let's put in the name of a variable, x. Let's print the size of x. Hey, it gave me 400. This is great. I can ignore everything that was just said in class because size of is smart. X is an array of 100 integers. Integer takes 4 bytes. X is 400 bytes. Yeah, size of gave me that. No problem. All right, let's pass x to our function. So I'll do step to step into our function. Now I'm inside my function. The argument I passed was called what? It was called arg. Let's look at the size of our argument. It's 8. It's the same array. It's got 100 integers. But now Sizeof is telling me this thing is only 8 bytes. And this is where you can get into trouble. So why is size of x 400, but size of arg, which is the same as x, only 8? because Sizeof really wants to deal with a type of variable. And the fact that you can do Sizeof on X, I kind of consider a bug. That would start a long-running war on Stack Overflow, I'm sure. But the problem is, up here, when we say integer x 100, the compiler knows how big x is. It knows an integer is 4 bytes. It knows I've got 100 integers. X must be 400 bytes. And Sizeof will happily tell you size of x is 400.
But it doesn't know that distinction inside a function.
Doesn't know that distinction inside a function, because what did I pass to the function? I passed by value an address. An address that happens to point to an integer, happens to point to 100 integers, but in this function there's no way to know that. Because I could have said integer x bracket 1,000, and when I call my fun, the argument's going to be exactly the same as it was when it was 100. So if I ask for size of arg here, all I can do is say it's a pointer to an integer. Pointer is 8 bytes. And so Sizeof gives me 8. Okay, why am I spending time on this? Everything we do in this class is going to be built around the idea of dynamically allocated memory. We're going to build these structures starting with lists in PA2. We're going to take pieces of memory and say, okay, give me a piece of memory. I'm going to store a node there. Give me another piece of memory. I'm going to store a node here. And now I'm going to take that first node and point to the second node. And if you don't do that really, really carefully, you're going to get seg faults. And this is really hard to figure out where the seg faults are, because it depends on the inputs you put to your program. It also depends on luck. You may end up with something pointing to a location that this time when you're running your program is available. And the next time you run it, that location may not be available. And so you may do the exact program, the exact same inputs, 5 times, and 3 times it works, and 2 times it seg faults. So errors with dynamic memory allocation, really, really, really tricky to debug. And this is a common issue that leads to those kinds of errors, because I think I'm allocating 100 times 4 bytes, but I'm actually only allocating 8. So I don't have enough space for my array, but worse, the next time I allocate space, Malloc's probably going to give me space that I think is part of that array. And maybe I'm using this for like a buffer where I'm getting input, and now depending on what the person types in, the contents of my array has magically changed. Okay, so easiest way to deal with this, just make sure you put in a type of variable. So if you want to allocate space for an array of 100 integers, how do you do that? 100 times size of int. Ask for a little arithmetic and you've got a perfectly safe, rock-solid way to get space for 100 integers. And if you're writing this statement anyway, integer x bracket 100, and you want to allocate space, you know how big it is. All right, we got 120 seconds. Let me give you something to contemplate. So, PA2, our nodes are going to be a little simpler. We're not going to deal with the valid field because we're going to let the operating system give us nodes and release nodes. So our nodes are going to have 2 pieces. It's still going to have a data piece. That's the number we're storing in the list. And it's going to have a next piece, which is where that link to the next node is pointing. What do you think the next piece is going to be? What type of variable? It's going to be a pointer, but what should it point to? A struct node. And that may feel a little weird, but it's perfectly safe. Because we're not saying a struct node has a struct node. A struct node has an address in it. Next is just an address. Happens to be pointing to a struct node, but that doesn't really hurt anything. So the node itself is actually going to contain the address of the next node. And that node is going to contain the address of the next node, and so on. And when we're at the end of the list, instead of putting an address, we'll need a magic address that we know is not valid. That's going to be what we call null. It's a predefined symbol. It's equal to 0, and we can use it as a flag just like my null. All right, so we'll start from here tomorrow. We'll go through all of the details of what a list looks like, and we'll do a baseline on these weird C notations and make sure we're all kind of on common footing with that. All right, so we'll start there tomorrow.